Let's start by looking at some examples of how energy changes from one form to another. When a car engine runs, it converts chemical energy stored in fuel into mechanical energy that moves the car and heat energy that is released. Trees use sunlight, which is radiant energy, and convert it into chemical energy through photosynthesis. Hammering a nail transforms mechanical energy from the hammer's motion into deformation energy in the nail and also produces some heat. In a thermonuclear reaction, nuclear energy is converted into radiant energy, like light and heat. An electric mixer takes electrical energy from a power source and changes it into mechanical energy to mix ingredients along with some heat. Similarly, a lamp uses electrical energy and changes it primarily into radiant energy for light and also heat. These examples help show how energy is not lost but changes form depending on the activity. Let's move on to exploring the different forms of energy involved in doing work. Work is essentially the force applied over a distance. There are three key types of energy related to work. Kinetic energy, which relates to the motion of an object and is calculated using half the mass times the velocity squared. Gravitational potential energy, which depends on an object's position in a gravitational field and is found by multiplying mass, gravitational acceleration, and height. And elastic potential energy, which is stored when objects are deformed, such as when a spring is stretched or compressed, and is given by half the spring constant times the deformation squared. Understanding these forms helps us quantify how energy is transferred or stored in physical processes. This statement explains one of the fundamental principles of energy. It can't just appear out of nowhere or vanish into nothing. Instead, energy changes form or moves from one place to another. For example, the energy from the sun can turn into heat or light, or the chemical energy in food can be converted into motion when we move. Understanding this helps us appreciate how energy flows through different systems and why it's important to use it wisely. Let's look at how conservation of energy works in mechanical systems without friction. At the highest point, the object has no kinetic energy because it's momentarily at rest, but it has maximum gravitational potential energy, which is mass times gravity times height. As it falls, this potential energy converts into kinetic energy. At the lowest point, the potential energy is nearly zero, and kinetic energy is at its maximum. By setting the initial potential energy equal to the final kinetic energy, we get mgh equals 1/2 mv squared. Solving for velocity, the speed at the bottom of the fall is the square root of 2 times gravity times height. This shows how energy transforms from potential to kinetic, allowing us to calculate the speed in an ideal system. When an object moves across a surface, part of its initial mechanical energy is lost due to friction and air resistance. This energy doesn't just disappear, it changes into internal thermal energy, which we can think of as kinetic and potential energy of the atoms inside the object. So the total initial energy equals the remaining mechanical energy after the object slows down, plus the thermal energy produced. Here, we see a clear way to understand efficiency by visualizing how energy is divided during a process. The total input energy is 100 joules, out of which 80 joules become useful output and 20 joules are lost as wasted or thermal energy. The calculation of efficiency is straightforward. You take the useful output and divide it by the total input, then multiply by 100 to get a percentage. In this example, that means 80 divided by 100, which gives us 0.8, or 80% efficient. This means that 80% of the input energy is effectively used, while the remaining 20% is lost, helping to quantify how well the system performs. When we talk about system boundaries, it's important to understand the difference between closed or isolated systems and open systems. A closed or isolated system is one where no energy enters or leaves, which means the total energy inside remains constant over time. In contrast, an open system exchanges energy with its surroundings, so energy can flow in or out. This interaction with the environment means the energy within the system can change based on external factors. Recognizing these distinctions helps us analyze how systems behave and respond to their environments more effectively. Let's work through this exam question step by step. We start with a 2-kilogram object falling from 5 meters high, and we want to find its speed just before it hits the ground. The key principle here is the conservation of energy, which tells us that the loss in gravitational potential energy will equal the gain in kinetic energy as the object falls. Using the formula mgh equals half of mv squared, we plug in the mass, gravitational acceleration, and height, then solve for the velocity. That gives us 2 times 9.81 times 5 equals 1/2 times 2 times v squared, simplifying to 98.1 equals v squared. Taking the square root, we find the speed is approximately 9.9 meters per second just before impact. This shows how energy conversion helps us determine motion in free-fall situations. To wrap things up, the key points to remember are that energy is always conserved in isolated systems, meaning the total energy stays the same throughout any process. Mechanical energy, which is the sum of kinetic and potential energy, is only conserved when there are no non-conservative forces like friction acting on the system. Friction, being a non-conservative force, causes mechanical energy to convert into thermal energy, which means mechanical energy is not conserved in such cases. When solving problems, it's helpful to use the strategy of setting the total energy at the beginning equal to the total energy at the end, adjusting for any energy transformations that occur along the way.